All right, so starting with our chapter 6 stuff, what we're going to talk about is this new concept of uniform circular motion. So we've so far just been talking about stuff that is traveling in a straight line. We've got all of our kinematics for that. We've got some forces stuff for that. Now we are going to discuss things that are moving in a circular motion. However, what we mean by uniform circular motion, we're still constrained a little bit here, right? We can't just move in any old way. For uniform circular motion, what we're going to have is constant speed. Obviously, we're not going to have constant velocity, but we are going to be moving in a circle, right, in a exact circular pattern. But we are not going to change speed. Obviously, if we're changing direction as we're going around the circle, we are accelerating. That's what we're going to have to get at here in a second. Um, but the speed is what's going to remain the same. So that's what we mean by uniform. Obviously, we are changing direction. We are moving around in the circle. We're not just sitting still or anything like that. But uniform circular motion just refers to the fact that we are going to be traveling in a circle at a constant speed, right? The speed is what is not going to change for this. So let's kind of talk about how this changes and what kinds of new quantities we need to talk about with our kinematics and whatnot. So we're moving in a circle. So we're moving around in some place that looks like this. So one thing we're going to know is if we want to describe where we are on the circle, we can actually do that with an angle, right? So what we're used to doing is just our raw position, right? We just have some sort of distance that we're describing, our x, however many meters. Now what we're going to use is we're going to use a combination of r, the radius of the circle, um, theta, right? The angle, how far around the circle we have traveled, our angular distance, right? Our angular displacement, we can call it. And we also need to talk about this quantity called s, which is the arc length that we have traveled. So what are the different quantities that we have? We have r, theta, and s that are all kind of going to work together to describe our position. Mainly what we want is our angular position, right? How do we describe this angular position? And how do we do it in a manner that kind of takes into account both how big this circle is and how far around, right? This actual curved distance here that we have, this is what our S is, right? So our angular position, as it turns out, we can describe in this very simple relationship. Our change in our angular position is going to be written as the actual change in arc length, the actual distance that we have traveled, right? This distance, this curved distance in meters, divided by the radius. So it's going to be this ratio of delta S, the arc length, to the radius of the circle. So this is actually going to be very useful. You might be thinking to yourself, how is this an angle, right? Is this, what do you mean, like in degrees or whatever? This actually is an angle, right? This delta theta equals delta S over R. This is your angle, and if you do this in meters and you keep this in meters, right? Just meters divided by meters or centimeters divided by centimeters, whatever. As long as these are the same unit distance, the units will cancel, right? We just have this ratio, but this is then actually an angle in radians, right? So in this case, right, this is why radians are so useful, right? If I just have my arc length, if I've traveled, say, I don't know, 1 meter on this arc length here, and let's say I have, a radius of 5 meters or whatever, I can calculate my angle in radians by saying it would be 1 meter divided by 5. That'd be 1/5 radians, right? That would be my angle, right? So how does this work? How does this actually translate to the angles that you're used to? It works very nicely, right? This is why radians are so nice, right? We already have um, uh, our angle in radians. You can solve for this arc length very simply. You don't have to worry about any sort of weird conversions with your degrees or anything like that. You just say delta S equals delta theta times R. The angle in radians times the radius of the circle gives you the actual physical length that you have traveled around, right? So of course, as you'll notice, this angle is just this ratio of, again, how far have we traveled divided by the radius of the circle. So what happens when we have traveled all the way around the circle? How far is that? What is that distance? So for one revolution, right, one revolution around the circle, your delta theta is going to be equal to what? We know it's one way around the circle is 2 pi. Where does that come from? Well, the actual distance that you've traveled is the circumference of the circle. The circumference of the circle is 2 pi r, right? The actual distance around the circle once is 2 pi r. That's your delta S divided by r. And of course, one revolution around the circle is 2 pi radians, right? So radians, you can also kind of trick yourself. Radians is the term that we use, but it really is, this is just a ratio, right? So it is a unitless quantity, so we don't have to worry. This is why it makes converting between our radians and whatnot and everything else much easier, right? So we can say 2 pi radians. This is also going to be equal to 360 degrees if you're curious, right? So now when I've gone all the way around, I've either gone 2 pi radians, 360 degrees. If I go halfway around the circle, right, I've gone pi radians or 180 degrees. If I go a quarter of the way around the circle, then I've gone, divide this by 4, you get pi over 2. So that's your pi over 2 radians, right, and so on and so forth, your 90 degrees, however you want to think about it. If you're curious, 1 radian is equal to about 57.3 degrees, right? But yeah, so this is why radians are very useful. It's just derived from this ratio of how far around the circle you've actually traveled divided by what the radius of the circle is. And of course, they're nice and useful if you take your angle in radians, you multiply it by the radius of your circle. That will tell you the actual arc length, the actual distance that you have traveled, right? So this is all nice and everything. This kind of tells us how we can talk about our angular position, right? We have our angular position is just going to be our linear position divided by the radius. We also have an angular velocity that we're going to be wanting to talk about, right? So again, if this is describing where I am in terms of angles, I can also describe how I'm moving in terms of angles, and the letter that we're going to use for that is the Greek letter omega, right? So this is the Greek letter theta. We use the Greek letter omega. It looks like a W, but it's kind of curved on the bottom. So we have our Greek letter omega is our angular velocity. And this is just simply going to be defined the same way we're used to. Say instead of delta x over delta t, we have delta theta over delta t. So of course we can write this in terms of the units that we're more familiar with. We know delta theta is delta s over r delta t, right? So delta s over r, this is theta, then we divide that by delta t. What is delta s over delta t? That is a distance divided by time, right? That is the actual speed around the circle, right? This is how many meters you're covering in a certain number of seconds. So the angular, just like we have our angular position, is delta s over r. Our angular velocity is our linear speed divided by our radius. Again, no other fancy units that you have to keep track of if you just work in radians, right? This just taking the actual speed that you're moving divided by the radius of the circle. If this is in meters per second and this is in meters, right? Now what you have is your units of radians per second, right? So if you do 1 revolution, that's 2 pi radians per second, right? So, and this actually works out very similarly, right? So we have instead of our position, we have our angular position, it's delta s over r. Instead of our velocity, we have our angular velocity, it's v over r. We also do have an equivalent angular acceleration. So this one actually is not going to show up in chapter 6 just yet. We're going to wait a little bit longer. I'll kind of explain why, but I do want to show it to you now, just so you can kind of fill in this and make all the different connections between our angular and our linear quantities. So we have our alpha, our Greek letter alpha is what we use for angular acceleration. Alpha is just going to be delta omega divided by delta t, right? And so this, of course, is going to then be, just say delta v over r delta t. So this is, of course, delta v over delta t is what? This is your acceleration. However, it's actually not your entire acceleration. Why is that? Let's get into this. I'm going to put this subscript on it. So this is a subscript. I'm not doing a times time. This is a subscript. This is just tangential acceleration is what we're going to call it. The tangential acceleration divided by the radius is your angular acceleration alpha. Why am I specifying that this is tangential acceleration? I have just delta v over delta t. Why isn't this just my full acceleration? So when we're undergoing this uniform circular motion, there are 2 different types of acceleration we have to worry about. If we're undergoing uniform circular motion, right, if we're traveling at this constant v, right, if our v is not changing, does that imply that my acceleration is 0? Well, my tangential acceleration is not 0, but we know there is also the centripetal acceleration, which we'll get to here in a second, which we'll have to derive. The centripetal acceleration is based upon the fact that I am changing direction, right? So when I'm going around the circle, I am constantly changing direction. That is associated with my my centripetal acceleration. However, if I speed up or slow down, then that has to do with my tangential acceleration, right? So essentially, I can accelerate in a couple different ways. So this alpha is based on tangential acceleration, but of course, as I said, for uniform circular motion, we have the case of alpha is equal to 0, right? So this is always going to be true because our delta v is, right, our actual change in speed is also going to be equal to 0. So again, This is why it doesn't show up in chapter 6. We will come back to this. Oops, sorry, let me make sure I'm not writing off the page. We will come back to this in later chapters when we talk more about rotational kinematics. As it turns out, we have our position, our angular velocity, and our angular acceleration. You can actually write all of the same equations that we had before with these units instead, because we just have delta S over R, we have V over R, we have a T over R. You can write all your 4 kinematics equations. You can do it for the angular cases. We will do that in a later chapter. For now, we are going to focus on the case where we have uniform circular motion, though, right? Where uniform circular motion, we have our alpha is going to be equal to 0. So we do need to know what all these quantities are. It'll be very important to understand all of them. But for now, the main things that we're going to focus on in this chapter are we're going to keep track of our angular position, and of course, we also need to keep track of our angular velocity. So this is the tangential acceleration. This one kind of I think is the most intuitive to understand. It just has to do with speeding up and slowing down. That's what you're used to when you're talking about acceleration. But as I said before, there is another type of acceleration called our centripetal acceleration. And so we need to derive that and figure out how we can talk about our centripetal acceleration. So again, what is our centripetal acceleration? It's going to be the acceleration associated with the fact that we are changing direction, right? So when we're undergoing uniform circular motion, we are traveling in a circle, we are moving at a constant speed, but our direction is constantly changing, and therefore we know we are accelerating. So we have our centripetal acceleration, and the symbol that we're going to use for that is A subscript C. So A subscript T is our tangential acceleration. A subscript C is our centripetal acceleration. So let's figure out what that is. So let's take a look at our circle again that we are traveling around, right? We're undergoing uniform circular motion. And so we have something that looks like this. So we're traveling around in a circle. We're moving at a constant velocity. So I can say here at this point in the circle, I am traveling at some speed v, right? v1. At this point in the circle, I am also traveling at the same speed, but I'm moving in a different direction, right? My velocity has changed, and we need to figure out how that velocity has changed in that time. If we can do that, we can figure out what our centripetal acceleration is, right? The speed is the same, the direction is different, so we know that the velocity has changed. So what other quantities do we want to keep track of? In this case, of course, we have our delta theta. We also have 2 more things that we want to talk about. We have this straight line distance, right? We have this is the radius, this is also r, and then I'm going to call this delta r, right? Now, we also have this arc length that we need to pay attention to, which, of course, as we know, we already defined, is delta s. So these are different quantities that we want to keep track of. We want to make sure we understand what these all mean. R is the radius of our circle. V1 is my velocity at this point as I'm going around the circle in this direction. V2 is my velocity at this point as I'm going around in this direction. Delta r is the actual distance between the 2 points, right? The displacement, I guess I should say, and delta s is the distance traveled, right? Delta r is our displacement, delta s is the distance traveled. So with this, we can actually start to derive what this centripetal acceleration is. How do we get about that? We want to figure out what this change in velocity actually is. So let's actually set up a triangle for this, and we're going to do some geometry here. So this V1 and V2, let's make a triangle out of those and see what this delta V is. So V1, again, this isn't quite right, but it's off at some angle like this. V2, we can say, is off at some angle like this, right? The length should be the same, right? The speed is the same, and the difference between these, just doing my simple vector addition that we have, just my visual vector addition, right? V1 plus delta V has to get me to V2, so this is delta V, right? Whatever this small kind of vector is that gets me from, if I add it, if I take V1 plus whatever change in velocity that I have, my delta V, then I get to my V2. So my velocity has definitely changed, right? The speed is the same, but my velocity is obviously changed in this direction, right? I have changed, I am moving in a different direction at this point than I was at this point. But either way, we can do this. We can set up this triangle. We have V1, we have V2. These are the same length. Then we have some other vector here, delta V. Delta V in this case is not the same length as V1 and V2. We're actually going to see that's pretty small in this case. But just to be clear, V1 and V2 are the same length, and delta V is different, right? Okay, so we have this triangle. We can also say we have a triangle that looks like this. In this case, we have R on each side, and delta r here, right? And so, as it turns out, these are what's called similar triangles, right? So they're different sizes, but the ratios all stay the same, right? We can say, imagine this one's pretty small, maybe this one's pretty big, or whatever it happens to be. It doesn't matter. The important part is that the ratios are the same and the angles in them are the same, right? And so we can assert that because, again, here's my r, here's my r, here's my delta r. My v is always just going to be perpendicular to the r. Here, in this case, v2 is perpendicular to this r vector, right? v1 is perpendicular to this r vector, right? I didn't quite draw it right. I wasn't quite good enough with my perfect circle, but it's close. So this v1 is perpendicular to this r. This v2 is perpendicular to this one, and so this angle between here, between v1 and v2, will be the same as this angle between these two different r vectors that we have, right? So these are similar triangles, and so this lets us write some very useful ratios. So what I can say is this ratio of delta v over v, right? And in v1 or v2, it doesn't matter, the magnitude is the same. So delta v over v is going to be equal to delta r over r. Now, what we can do from here is we can say, let's imagine, let's do this for a very small angle. Let's do this from one instant to the next, right? So I know I've drawn this kind of big, but let's kind of just imagine I want to look at what the change in velocity is from one instant to the next, right? So you can imagine, if I draw a different circle, if I draw it like this, this point is my first point that I want to see. This is my first velocity that I want to measure. And then my second point is immediately after it, just barely any time has passed, right? There's this very tiny difference, right? The smallest amount of time between them, the smallest amount of space between them, as you can imagine, just between from this point to this point. But there is still some sort of minuscule change in velocity, right? So again, just take this triangle, shrink it down as far as you can, and just it's the smallest it can be while still forming this triangle. What can we then say about delta r? In that approximation, if we make this angle very small, right? We make this delta r very small. What we can see is that delta r actually, in this very small approximation, if we just travel one instant forward in time, right? Delta r is equal to delta s, right? So this diagonal length from one point to here and this arc length, actually, as we shrink this down, we make this triangle smaller, these become the exact same length in that approximation, right? So when we do that, what we end up with is this. We have delta v over v equals delta s over r. So now I can write delta v is equal to delta s times v over r. So how does this help me? Well, what happens if I divide both these sides by delta t, just the amount of time that has passed? What do I have here? Delta v divided by delta t. This is now my centripetal acceleration, right? This change in velocity over change in time. How's my velocity change? This is the velocity change associated with my direction change, right? So this delta v over delta t is going to be a sub c, right? So we have a sub c, my centripetal acceleration, this is what we wanted to drive, is equal to what? We have delta s times v over delta t times r. What is delta s divided by delta t? It's also v. So what we end up with is our centripetal acceleration is v squared over r, right? And so this is what the centripetal acceleration is. So there is some sort of acceleration associated with this change in direction. In this case, it is this quantity here. It is v squared divided by r. So if you're traveling in a circle at a constant speed, you do still experience some acceleration, right? You have this acceleration. It's dependent upon how fast you are going, right? The faster you're going, the faster your direction is changing, right? The faster you're getting around the circle. But it's also dependent upon the radius of the circle. If you're going around in a very large circle, right? If you're just moving very slowly around in this very large circle, or even if you're moving quickly, but the circle is very large, you're not changing direction very quickly, right? So a higher v will give you a higher centripetal acceleration, and a bigger r will give you a lower centripetal acceleration. This should kind of make sense to you, right? If you're going really quickly around, right, really fast in this really tiny circle, then obviously you're changing direction very quickly, and so you are accelerating very quickly, right? You have a higher centripetal acceleration. So why do we care about this? How does this relate to what we were talking about before? This also, of course, leads to the idea of the centripetal force. This is, of course, just going to be the mass times the centripetal acceleration, right? So if I have some object, say you have a car on a road or like some sort of rock on a string or anything at all, or a planet in orbit, or satellite in orbit around the Earth or anything like that, the moon in orbit around the Earth, anything like that. We'll get to that later on this chapter. Anything undergoing this circular motion at a constant speed, the net force on it has to be equal to that object's mass times the centripetal acceleration. So of course we know then the centripetal force will just be mv squared over r. Whoops, I'm off the page. There it is. Okay, so um, let's make sure we understand this though. This is the net force on the object. The centripetal force is not some sort of extra force. It's not like friction or gravity or anything like that. This is the net force, right? When we say for some object undergoing uniform circular motion, and I write F net equals ma, right? I write Newton's second law. In this case, the A, right, is this. If this object is traveling in a circle at constant speed, you know right away the A is mv squared over r. So, for instance, we can just do a quick example. If we have a car going around a circular turn, right? It's moving at a constant speed. You would have gravity, friction, and the normal force. I'll draw it here. Let's say we have, here's a top-down view of my car as it's going around this turn, right? And then of course I can also draw it from the back, right? If I'm looking at the car from the back, and it's kind of turning to the right here, as it's going into the page is the direction of this car, and it's turning off to the right in this direction. So this is the top-down view, this is the back view. My forces would be what? I would have mg, I would have the normal force, and I would have friction. These are all the three individual forces acting on this car, and when I do my F net equals ma, I would be able to write this. I would say, let's see, so I have mg plus, so I have minus mg is the negative direction, plus the normal force. This is equal to 0, right, since I'm not accelerating in the y direction. And then this is what I would say for the y direction. And then, of course, for the x direction, what would we have? We would say the frictional force is equal to mv squared over r, right? So again, the three individual forces that I'm adding together, normal force, gravity, and friction, but my net force that they must add up to be equal to, my F net equals ma. In this case, since it's going in a circle at a constant velocity, the acceleration that I set it to must be mv squared over r, right? So don't get confused. The centripetal force is not some sort of extra other individual force. This is your ma part of your F net equals ma, right? So we'll see a bunch of examples with these. We'll have cars going around. We'll do all kinds of things with that. We'll see when they start to slip and everything like this. But for now, we can just say again, when we have some sort of object moving in a circle at a constant velocity, the net force must be equal to mv squared over r.